We do know what the potential energy is at the bottom here, because we know today what the Hubble constant is today.
Oh, the Hubble,
That's very small.
What about that?
We also suspect, and there's some evidence, that the potential energy up here was very much larger, and that the universe, that the Hubble constant was very much larger. In other words, that the doubling time of the universe was many orders of magnitude larger than this one doubling every 10 to the 10th years. In fact, with standard cosmological numbers, this inflation took place with a time constant of 10 to the minus 32 seconds or something like that. So it's kind of crazy. I mean, this is a crazy picture. This is a crazy picture. The amazing thing is that
I agree more with him. How about you? What are you thinking, Charlie? You're listening to it?
Gradually drifted down here and came to the edge and went down to here. The expansion that took place up in here is called inflation. It's called inflation. Where did the Big Bang happen, incidentally? The thing that we normally call the Big Bang. The Big Bang happened after we got pretty much down to here. After we slid over this edge, the Big Bang, meaning to say, what I mean by the Big Bang now is the surface of last scattering. The surface of last scattering was very late in this picture. It happened well after the universe settled down here.
You believe every word he says. Are you listening? I am. You're listening? I mean, he's not even speaking about the Cambrian folk. Are you listening? Did you put it on so I should listen? Come on, talk to me. Hello? Hello? This man is not a big scientist at all. He's just sort of a blowhard. You mustn't believe what he says. I don't. But it sounds rather interesting. I would listen to it if I knew it was on the telly. Are you on the telly or the radio?
So the Big Bang and everything we actually can observe about cosmology was down in here. Right? But before the Big Bang happened, this period of exponential inflation took place, according to theory.
Inflation.
And during that period, the universe stretched itself out so much that all of the wrinkles disappeared, if you like.
Yeah,
so that means that the universe at the time of the Big Bang, or the time of the surface of last scattering, was already stretched out by many, many powers of E. How many powers of E? That we don't know for sure.
E?
The wrinkles are mainly wrinkles in the...
You've got to get a better word than E.
Scalar field, then.
And also the gravitational field. Also the gravitational field, yeah. In other words, the shape of space and its curvature might have been fluctuating, but also phi.
What's the x-axis? Is that t or is it phi?
Phi. Here, in this.
Are you profiting well
field
from
phi.
this?
This is the potential energy as a function of the field phi. The field phi can depend on time.
It's not like a thing called
As the universe rolls down this hill.
Well, it's sort of acts like a time parameter.
Like a what?
It's acting like a time parameter here because you've got a monotonic function that's...
It is, in fact, acting like a time parameter.
True. Time parameter.
This is true. Time parameter meaning to say it's monotonic.
Who is this man, this professor of nothing talking? Who is he? What's his name, Charlie? Where's he from? Whatever his credentials.
All we know is that we're living in some place where the potential energy is not quite zero. Yeah. Nothing in our experience tells us very much about here. Looking back in the past, we discover something that looks like a motion like this. We're going to come to what the observational evidence for this is, but
this may be a bad analogy, but when you're looking at gravitationally derived potential energy, it's a function of position, but there's only potential energy in the presence of a gravitational field.
I don't think think so. Gravitation to what?